Hi guys, in today's video we're going to look at 5 main areas. First we're going to look at the resultant of 2 forces, then we're going to look at the resultant of 3 forces, then we are going to have a look at resolving a vector into its components, then resolving a vector into perpendicular components, and finally we're going to have a look at the proofs for x equals v cosine theta and y equals v times sine theta. So with that being said, let's get cracking. Okay, well first off, let's imagine we just have an object like this box, okay? And let's say there's somebody pulling on that box with a certain force. So if you pull on the box with enough force, you'll move it, and it will start to move in the direction that the force is applied. Let's say that there's another person also pulling the box in the opposite direction. So your force is still there, you're still pulling the box to the right, but this other person has also started pulling and is now applying a force in the opposite direction. So what can we deduce from this? Well, if the box doesn't move, if the box stays where it is, then you can safely say that the two forces are equal. That the force in one direction is equal to the force in the other because it's not being accelerated. So the two forces are balanced and the object doesn't move. And like we discussed last lesson, if you want to get the resultant of these two forces, it's just the bigger one minus the smaller one. So this box will move 7 newtons to the right because the force to the right is stronger than the force to the left. But we're going to look back again at the situation when the object is at rest. So when it's either not moving, or if it was moving, it's moving at a constant velocity. But let's just go with the idea that it's not moving, it's staying stationary. So now let's look at trying to resolve 3 forces. So again, let's imagine we've got an object, just like the box. Now this time let's say we're looking down on it from above. So let's say that there is one force, I'm going to call this force 1, that's pulling it to the right. And there's another force called force 2 pulling it up and to the left. And there's a third force called force 3 putting it down and to the left. Now presuming that the box isn't moving and that it's staying in the same place, or if it was in motion it's moving in at the same kind of constant velocity. So just presuming that it's at rest, that it's not moving. If that's the case, we know that these 3 forces are balanced, that there's no net resultant force on the object. So if I want to find the resultant of the 3 forces, here's what I do. First off, I could find the resultant of any 2 of these forces. Like if I wanted to find the resultant of F1 and F3, it's going to pull down in this direction. That's the resultant force of just force 1 and force 3, ignoring force 2 for a minute. But that resultant force between force 1 and force 3 will be in exactly the opposite direction to force 2, and it will be exactly equal in magnitude. It's pulling against force 2 with the same amount of force. And again, we can deduce all this because it's at rest. So the resultant of any 2 of those forces is directly opposite and equal to the other third force. Next, we're going to look at resolving a vector into its components, which means breaking it down into two vectors that make it up. But first, let's kind of recap what we did earlier about combining 2 vectors together to calculate a resultant. Previously, we were looking at how to add 2 vectors to calculate a resultant. So for example, if I wanted to add this vector to this one, I just put them together and see where the result will bring me. So bring the tail of that to here. And the resultant of those 2 vectors would be the line that joins them, okay? Now we've done loads of those kind of examples where you move the 2 vectors to calculate the resultant. And the resultant would be one vector that would do the job of the 2 if they were combined. So far so good. That's kind of what we were talking about before. What we're talking about now is you can do that in reverse. So by which I mean, let's say that I've got a vector just gone up like that. If I want to break it down into components, I just want to find 2 vectors that would sum to give me this one. So for example, I could say, let's say that's one vector, and let's say that's another. These are 2 components that would add up to give me the net effect of this vector. So for example, if I first move in this direction by this much, and then in this much, across here by that much direction, I'd end up in this position. So I can resolve this original vector, that's the one we're talking about, into 2 vectors, 2 of its components we call it, 2 vectors that would give me the effect of that one. Now you've probably already twigged that there's a never-ending supply of these. I could have gone, alright, what if I went down here by that much, and then I went up here by that much. That's totally fine too. These are 2 other components that will give me that resultant vector. Totally fine. And while you can resolve a vector into any 2 components, it's not terribly useful to just do it into random ones. It's much more useful. So let's say that's the resultant vector we're talking about again. It's called V. It's much more useful. Instead of putting it into 2 random vectors, to put it into two vectors that are at right angles to each other. So for example, the kind of most intuitive one, the one that should jump out at you, okay, well this vector is like if I had a vector going up by that much, and I had a vector going across by that much. These are two components that are at 90 degrees to each other. That's a much more useful way of resolving this vector into components. It's not the only possible 90-degree arrangement, so just get rid of those for a minute. I could also have done it like, I don't know, let's say like, let's go even mad. Sorry, my brain's a little wobbly today. Let's go like that. You could have resolved it into these two component vectors, which again would sum to give the resultant, both perfectly viable. So resolving a vector into its components is fine, but resolving them into perpendicular components, so components that are at 90 degrees to each other, is going to be much more useful. So most of the time you're going to be given a frame of reference around which this will make more sense. So let's say, for example, that that's my vector, okay? While you could choose any two components that are at 90 degrees to make it up, more often than not, you're going to be given a kind of an alignment to use. So for example, the most common would be the x and y axes. So the x-axis is going across, y-axis goes up and down. So it's much more common to kind of relate this to the x and y axis. So let's say that's our resultant vector we're trying to find. Let's make that the hypotenuse of a triangle, with the bottom of it being the x-axis. It's going directly across. And the top, the vertical component being along the y-axis. That's kind of much more useful. So last time we said that two formulae we're going to use would be, if I'm trying to find how far across a vector goes, or how far up a vector goes, I can use these two equations. That the x component is equal to v multiplied by cosine theta, and the y component is equal to v multiplied by cosine theta. And remember, if you're wondering what is v, v is the magnitude of the vector we're looking at. Okay, so in a few minutes, I'm going to do this in a bit of a backwards way. I'm going to look at a proof of it first, and then I'm going to kind of explain why you multiply the whole thing by v. Okay, so here we go. Okay, we're going to start off by trying to prove why x is equal to v times cosine theta. And by the way, if you're wondering, did something weird just happen up the top corner, and this changed, it did. I'd inadvertently written cosine theta for y, which is wrong. So it's x is v times cosine theta, y is v times sine theta. So let's prove this first one first. Y is x equal to v times cosine theta. So just to remind ourselves, if we're trying to calculate the x component, y is it the magnitude times the cosine of theta. All right, let's prove it algebraically. So first off, what is cosine? Well, if you remember my way of remembering it, or whatever way you were taught, I go silly old Harry chased a horse through our attic. So cosine is a over h, adjacent over hypotenuse, which is the ratio of the sides. And in our case, with our triangle we're looking at, the adjacent to the angle theta is x, and the hypotenuse is v. So the cosine of the angle theta is x over v. And then just doing a little bit of algebra, let's multiply both sides by v, which will give me v times cosine theta is equal to x, which is what we're trying to prove. And that just went off the screen, just pushed it up a little bit further. So we can use a very similar method to prove why y is equal to v by sine theta. Let's do that now while we're at it. So y is equal to sine theta, v sine theta is what we're trying to prove. So let's go with what is sine. Well, sine is opposite over hypotenuse. So cosine, yeah, so sorry about that. We're looking for sine. Let's talk about sine first. Sine is opposite over hypotenuse. In our case, the opposite is y. So the sine of this angle, sine theta, is equal to y over v. And using the exact same logic as before, let's multiply both sides by v. So v multiplied by sine theta is equal to the y component of the vector. Bob's your uncle, things are proved.